We're gonna, oh yeah. Okay, you guys, we're gonna talk about adding vectors graphically. You've already figured out on your own how to add vectors in component form. You just added the x's to the x's and the y's to the y's. I think most of you figured that out, on the very first problem because you looked at the answer on the back of the book and had your answer match it. But I need to make sure you guys understand how to add vectors graphically. I think I may take this opportunity to talk about the components of vectors and why they're so important, the x and y components. Then we're going to talk about getting the unit vector tangent and normal to a curve, and that's going to involve getting the first derivative. And then finally we're going to talk about the dot product. This is a process we use to find the angle between two vectors. Those of you who had Mrs. Lofgren last year, did you guys learn about the dot product last year? Okay, so you guys are good. So essentially, again, it's just me and Kylie. Yes?
Is that the one where it's like a three vector where you have to multiply it by this certain number?
You're talking about cross product, maybe?
Cross product.
Yeah. No, believe it or not, we aren't going to do cross product in this class. What's that?
Never mind.
Okay, yeah, cross products is actually an incredibly important concept, but you'll end up learning that, in either your multivariable calculus class, which is the one after this, or you'll learn it in your calculus-based physics class, where you'll learn that torque is no longer force times distance times sine of theta. You'll learn that torque is R cross F, where cross is the cross product, So in one of those two classes you'll learn about cross products, but for some reason it's not in my curriculum, so I ain't going to teach it. But I do want to teach you about dot product, which is actually pretty easy and pretty basic, Okay, great. So let's get started. Adding vectors graphically. Adding a vectors graphically. Suppose I start here and I walk a ways and I end up there. And then I decide to walk a little bit farther and I end up there. And I want to know where I ended up. I'm not interested in how I got there. You know how they say it's not the destination that matters, it's the journey that matters. Well, in this case, it's only the destination that matters. I don't care how I got there, okay? And so I want to know where I am. And the way you get where you are is to draw that vector there. And so generally, if you want to add two vectors, you're going to put the initial point of the second vector onto the terminal point of the first vector, and then connect the initial point of the first vector to the terminal point of the second vector. Just like what I did here. And that gets you a vector that tells you what your progress was. You started there, you ended there, this is what you accomplished. This is the progress you made. How you got there is irrelevant. All we care about is what the final product is. You started there, you ended there. That's what you accomplished. And this is true not just for displacement, not just for distance, where you started here and ended there. It's also true for any other vector quantity. Let's look at forces. Suppose I have some big object, okay? And suppose I've got several forces acting on this object. F1, F2, and F3. And I want to know what the net force on this object is. The net force. That is, how much force am I getting and in what direction if I had one single agent exerting the sum of those three forces. Because this force is going to make this rock want to go down, this force is going to make it want to go that way, this force is going to make it want to go that way. Well, what if all three forces are acting? What does this object do? And the way I can find that is by adding these three forces together. So here's what I do. I'm going to take F1, okay, and maybe I'll just leave it there, or should I bring it down here? Because remember, vectors can be moved. As long as you keep the same orientation and the same length, I can put a vector wherever it's convenient for me, okay? So maybe I'll put this vector at the center of mass of this object. Because we know that in physics, all forces act, are said to act at the center of mass of an object if you want to find its linear acceleration. Okay, so here's the center of mass. So the first force I'm going to put there is F1, and F1 looks to be about that long. Okay, so here's F1. Alrighty, and then F2. I'm going to keep the same orientation and the same length, but put the initial point in F2 at the terminal point of F1, just like I did when I walked from here to there. So I take the and the So it looks like I'm going to put that guy there. So this is F2. And then finally I've got F3. So I'm going to take F3 and put it there. Did I just mess that up? So it looks like F3 is going to go like this. That's F3. And so the sum of those three vectors gets me this. This is the net force. Essentially, one single agent exerting a force of that magnitude in that direction is going to give me the same result, linear, with linear motion, not rotational motion, that's a different story, but with linear motion, I get the same result with this this guy, F1 plus F2 plus F3, okay? So if I can summarize adding vectors graphically, you put the terminal point of V2 onto, I'm so sorry, you put the initial point of V2 onto the terminal point of V1, then you connect initial point of V1 to terminal point of V2. That's V1 plus V2. You guys ready to do it on your own? Okay, I'm going to give you three vectors to add. Here they come. And when you do it on your paper, you'll just kind of estimate. Here's V1, here's V2, and here's V3. Go ahead and do V1 plus V2 plus V3 now. And they could be displacements, they could be forces, they could be anything. But just put terminal point to initial point to terminal point, initial point to terminal point, and then finally you'll connect the initial point of the first guy to the terminal point of the last guy. Good luck. Yes. Sure. Where's your phone? Are you serious? Oh, that's not stupid. I think it's great. It might be the best thing they ever did. You'll start doing art and music and reading literature and go, oh my God, my life is so rich now that I don't have a phone. So yeah, go. Yeah. I think everyone, is anyone giving up anything for Lent? Okay. What are you giving up if you want to share it? YouTube and what?
YouTube cookies and chips.
YouTube cookies and chips. And what are you giving up?
I gave up social media and I decided to read the Bible.
Good for you. Yes, did you notice both of them involved that thing? Yeah, YouTube, social media, yeah, that would be the huge, nowadays yeah, I would totally give that up for Lent. If I used to give stuff up, but nowadays, absolutely. Social media, baby, that's what I would give up in a heartbeat. Yeah. Okay, well anyway, those are the three vectors. And so the sum is going to be start at the initial point of the first guy and go to the terminal point of the last guy. And so this red guy is V1 plus V2 plus V3. Yeah. Any questions or issues? How many people got that one right, more or less? Okay, many of you. Good. Great. Alrighty. Well, that's adding vectors graphically. I just might need to make sure you guys are okay with that. You know? I had to give up gambling for Lent 1 year.
Were you able to do it?
Yeah. Oh, yeah. Yeah, I mean, yeah, you do it. If you're going to do it, you do it. But it's weird because now I don't gamble anymore, but not for Lent. It's just because, I don't know, gambling just isn't a part of my life. It's weird. Weird how that happens. Okay, let's go ahead and get unit vectors, normal, tangent, normal to curve. And I'm going to define these curves parametrically, okay? And pardon me, I am going to get my notes. I was going to do it from my memory, but I'm losing faith in my memory, so I'm actually going to get my notes. Just 1 second. All right, great. Here we go. Unit vector is tangent to normal curve. Here's what you're going to do. Here's the two-step process we're going to do this. Step 1, find slope of tangent. Slope of the tangent line. And let's say the slope of the tangent line is b over a. It could be, 5 over 2, or it could be something like 1.74 over 1, whatever fraction you happen to get. And then part B, you're going to get the unit vector. And the unit vector is going to be a comma b over the magnitude of a comma b. Now the weird thing is, if you've got a curve, let's say you've got some curve, and you find the slope of the tangent right there. You find the slope of the tangent. So you go, okay, well, there's my unit vector right there. There's my unit vector, which is the unit vector that points in the direction of the tangent. I want you to see that it could also go in the other direction. You could also claim, hey, why can't it go in that direction? Wouldn't that be the same direction as that? I mean, it's the same line. And so I want you to know that you can actually get two different unit vectors that are tangent to a curve. You could actually just do this, have it be negative a, negative b over the magnitude of negative a, negative b. And that'll get you an answer too. So sometimes the book will actually say, give me two vectors that are tangent, unit vectors that are tangent to the curve, and this is what they're wanting. They're saying, hey, you can go that way or you can go that way, Well then, hey, let's go ahead and do one, okay? Here comes example number 1. And I have to say again, this is not that hard. X equals log natural of t, and y equals t squared plus 5. Find unit tangent to curve at t equal 3. Well, let's do step 1. Let's get the slope of the tangent. Let's get dy dx evaluated at t equal 3. but we know that when we're dealing with parametric curves, that's the same as dy dt over dx dt. And that's going to be evaluated at t equal 3. And so dy dt is 2t, dx dt is 1 over t, and then I plug in 3, and I end up with 6 over 1 over 3, which is 18. Which is the same as 18 over 1. So I've got a slope that's a rise of 18 and a run of 1, so I want to get the unit tangent, the unit vector. That unit vector is going to be 1 comma 18. The rise is 18, so the y component is 18 over the magnitude of 1 comma 18, which is going to get me 1 comma 18 over the square root of 1 squared plus 18 squared, which gets me 1 comma 18 over, what is 18 squared? 289, 324? 324, I think. Isn't it? Oh, I don't know. I'm going to say it's 324, whether it is or not. Add 1, and so that's going to be radical 325. So you could express your answer that way, or if you prefer, you could express your answer like this: 1 over radical 325, comma 18 over radical 325. And that would be fine as well. But I certainly wouldn't want you to rationalize the denominator. By the way, there's another one besides that one. What other, I mean, so we've got some graph, and frankly, I don't even care what it looks like, but I've got some graph where at some point, you know, the tangent line has a slope of 18. So there's my unit vector, 1 over blob, comma, 18 over blob, radical 325. There's my tangent vector. Could I get another one besides that one?
Yes.
Yeah, what would the other one be?
The one in the opposite direction.
Yeah, thank you very much, Daniel. The one in the opposite direction. This guy. Yeah, that guy. And so what would its coordinates be? Instead of 1 over 3 radical 325, what am I going to put here?
-1.
Yeah, good for you. -1 over radical 325 and -18 over radical 325. Yeah, like I said, just so you can get the same answer as the stupid book. By the way, what if they ask for the normal? What about the unit normal? Do I have to do a bunch more calculations? Or can I do something to those vectors to get the unit normal? What's that?
What's the unit normal?
The unit normal, that would be, instead of these red vectors, the unit normal would be the one that's perpendicular, the unit vector perpendicular to the graph, either going in that direction or going in that direction. How would I get the normal? That is the perpendicular. Yes, Zach? Yeah, beautiful. Absolutely. Yes, I'm not even going to elaborate on it. We're just going to go with what Zach said. Yeah, it'd be -b comma a. If the tangent vector is a comma b, then I need a negative reciprocal slope. If you're not comfortable just making that leap like Zach did, you can always just look at this. Where is that? Right there. You know, if the slope of the tangent equals 18 over 1, then the slope of the normal has to be the negative reciprocal. So it'll be -1 over 18. And now you get Zach's answer. You see? So if you feel more comfortable just taking the slope and doing the negative reciprocal of the slope and then doing all that a comma b stuff with it, that's fine with me as well. You know, just know that it could be either -1 over 18 or 1 over -18. So you know, you've got two choices for your unit normal, just as you had two choices for your unit tangent. So yeah, in this case, the unit normals would be either That was 1 comma 18, so this will be 18 over 325, radical 325 minus 1 over radical 325, or negative 18 over radical 325, comma 1 over radical 325. Either of those would be correct answers. Okay, you guys ready to do it on your own?
Sure.
Thank you. Whoever said sure, I appreciate it. X equals t squared plus 5t minus 12. Y equals 4t plus 2. Okay. Get unit, tangent, unit, normal at t equal 1. Good luck, you guys. Good luck. First, you're going to have to get the slope of the tangent, which means getting the first derivative, and then letter it. Then we're going to learn the dot product, and we'll be done. And I'm going to talk about components tomorrow when we learn about vector-valued functions. Then I'll talk about components, because it's better. Is everyone good today? Looks like it.
Karen's not here.
Oh, yeah. Thank you. Is everyone getting 4 7s for the slope of the tangent? Yay. So it's what, going to be, remember this is the y and that's the x. That's the rise and that's the run. So did anyone get that answer? You guys good? Okay, thank you. Okay, you guys good with that? And you could also rewrite this as 7 over rad 65, comma 4 over rad 65, which is, that's actually the way I personally prefer it. But I think the book, for some stupid reason, the book prefers 1 over rad 65. Oh, I don't know what the book does, but it's whatever, stupid book. But I think just go with that. And then the normal. Just switch them. Maybe if I call that tangent, I call that normal. And so it ends up being negative 4 comma 7 divided by rad 65. Or 4 comma negative 7 divided by rad 65. Okay? Well, hey. Any questions or issues with that? What?
Oh, no, I was thinking, because sometimes I draw my radical signs, like they look like almost like straight up and down, so they look like division signs.
Yes.
And I was just wondering if you ever get confused between the two. When not like on my tests.
No, because it's always unambiguous what the context is.
Yeah, because it's always, I've never written a division sign.
Yeah. I mean, I've had kids do their radicals. The biggest problem with radicals is the index of the radical. You know, like if you're doing a cube root,
Oh, yeah.
where you have to have the index right there, and sometimes kids will put that index just in crazy places, you know, where someone will do this, you know. And they'll go, well, that's a cube root, Mr. Shana. And it's going, well, that doesn't look like a cube. Okay, let's see what we got here. Oh, great book. Don't look.
Ooh, angel.
I don't like it. There you go. Okay. Here, I need to prove to you the dot product. This will take 5 minutes. I see you looking at the clock. Are we running out of time?
Yes.
No, we're not. We're good.
We're getting closer to that.
Okay, but here we go. Find the angle between two vectors and the dot product, okay? Do you notice I've got 3 vectors here? I've got vector u, vector v, and then I've got the vector w, which is the difference between u and v. You'll notice u and v are connected initial point to initial point. And I want to get the angle between 2 vectors that are connected initial point to initial point. That is essentially, I want to get the angle between 2 vectors in standard position, where both of their initial points are at the origin. And I want to get the angle between them. So this derivation requires that the 2 vectors be connected initial point to initial point. Okay, great. Well, then that third vector is vector u minus vector v, not u plus v. And I hope you can see why it ends up being u minus v. I'll do that, maybe let me do that on this side of the board. Let me just show you, because I didn't teach you how to subtract vectors, per se. I just taught you how to add them. But subtracting them just means adding the opposite. So now is the time when I'm just going to show you. And I'm hoping it makes sense to you guys that if I've got vector v and I've got vector u and I want to subtract u minus v, well, vector u minus vector v is the same as vector u plus the opposite of vector v. So what I'm going to do is first get the opposite of vector v, which would be the very same length, but just pointing in the negative direction. That's negative v. And then I'm going to take this guy here and put it there. So this is my u. And then it turns out that u plus negative v ends up being this vector here. Or maybe I should do this. Maybe this negative vector v, what if I'm just trying to figure out how to get the initial point here. And it's like, I don't know how I'm going to do that. U plus negative v. There's u, and there's negative v, so I get that. Maybe if I put my negative v like this. There's my negative v, and there's my u. No, that doesn't work. Well, I can't figure out how to do it, but anyway, God, what's my problem? I'm sorry, I'm struggling here. I'm trying to figure out how to get it so that when I do u minus v, it always ends up being a vector that if they're connected initial point to initial point, it's a vector where you start at the terminal point of v and go to the terminal point of u. And this is always going to be u minus v. I mean, there it is, but I had to put it over there. That's, I don't know, how to prove this to you. But anyway, just believe me that that's u minus v. I don't know, do you believe me?
Yeah.
That this guy here is u minus v?
Yeah.
I'm hoping so, because the whole derivation hinges on it. So here comes the derivation. First, law of cosines. I'm involved with the angle theta, so I got w. I'm going to call that third vector w. W squared equals u squared plus v squared minus 2uv cosine theta. That's the law of cosines. And then I'm going to substitute u minus v for that w. So now I got vector u minus vector v, quantity squared equals u squared plus v squared minus 2uv cosine theta. And of course you don't have to write this down, just watch and enjoy. Let's let u be u1, u2, let vector v be v1, v2, and vector w will be u1 minus v1, comma, u2 minus v2, because it's the difference of u and v. And so then I can get an expression for the magnitude of u, the magnitude of v, and the magnitude of u minus v. And then the next step is to actually substitute all of those magnitudes in. So I substitute all the magnitudes in. All right. So then I get this infinity of canceling. All of the u squareds, u1 squared, u2 squared, v1 squared, v2 squared cancel. And I divide both sides by 2, and I divide both sides by -1. And I end up with this. And then I solve for the cosine of theta. What's that? Yeah, please write this down. And then here's the weird thing. Math people, this ends up being such an incredibly important quantity, u1, v1 plus u2, v2, that they decided to make an entirely new type of multiplication that will get you that. And so they call that multiplication the dot product, or the inner product. And they define the dot product, u dot v, as being just the sum of the products of the components. U dot v is going to be u1 v1 plus u2 v2. And that's what a dot product is. That's all it is. You multiply the x components, multiply the y components, and then add them up. And that gets a special name. It's called the dot product. And it's special just because it shows up here in this formula. Yes?
The UV, those are the magnitudes of the UV, right?
Yes, yes. The absolute value thingies are the magnitudes. Yeah. Yeah, because essentially I solved for u1 v, did that thing. And there's the magnitudes right there. Okay? Because I got that from the law of cosines. And so there you go. You get the cosine of the angle ends up equaling this formula. So any question or problem on this before I make it go away? Or maybe I'll just give you the problem now. Here, get me the angle between, I'm going to give you a couple of problems. This should take you 30 seconds. Here's two vectors. V1 equals 1, 2, and V2 equals -2, 5. Get the angle between them. Alrighty? Just mindlessly plug into that formula. Cosine theta equals V1 dot V2. And by the way, the dot of a dot product has to be a really thick dot. It can't be a little teeny dot or it looks like normal multiplication. And this will be the magnitude of V1 times the magnitude of V2. So this will be 1 times -2 plus 2 times 5 over radical 5 times radical 29. The magnitude of V1 is radical 1 squared plus 2 squared, which is radical 5. So I end up with, what is that? 8 over radical 1, 45. Don't go yet. There's one more thing I need to say. One more sentence. But before I do that, just a second. Okay. So inverse cosine of 8 divided by radical 145. So I get about 48 degrees. Okay. Here's the last thing I need to tell you. What if two vectors are perpendicular? What's their dot product always going to be equal to?
90 degrees.
What's that?
90 degrees.
Okay, 90 degrees. So what's the dot product? What's the cosine of 90 degrees? 0. So what's the dot product always going to be equal to? Yeah, exactly. So that's the last one. If V1 dot V2 equals 0, then V1 is perpendicular to V2. All right, that's it. We're done. Bye-bye.